exciting panel coming up. And the panel is on the future of big data. Of course, we've seen what are the past, what's the present of big data since the morning. Future of big data will be moderated by Anand Rajaram. He's a co-founder of Cosmix, which was acquired by Walmart. And he's an academic, he's an investor, and he's an entrepreneur. And Anand will introduce the rest of his panelists. Take it away, guys.
Thanks, everyone. We have a terrific set of panelists here. Closest to me, we have Peter Norvig, Director of Research at Google, and one of the pioneers of using big data to do interesting things. Next to him, we have Subutai Ahmed, who's the VP of Engineering at Grok, the company formerly known as Numenta, using neuroscience to figure out the next generation of big data processing. And finally, we have MC Srivas from the CTO and co-founder of MapR, who's working at the foundations of big data. Right, so why don't we jump right into this? You know, throughout the day, we've been hearing a lot about big data. You all have been hearing a lot about big data, about both the hype and the reality behind big data. Now, in this session, it's about the future of big data. So I just want to get away from the messiness of the present and kind of jump ahead into a future that's maybe 5 to 10 years from now. And I'm going to ask our panelists to imagine what the future looks like 5 to 10 years from now and sort of gaze into the crystal ball and give me their answers. But before I get there, you know, what I'd like to hear from each of the panelists is, you know, how did you, how did you start working with big data? And can you give me your sort of favorite big data application, right? So that's my kickoff question. Peter?
OK. Let's see. I guess I got started in graduate school. I was working in natural language understanding. And I started working with small data. So I was working at parsing sentences, sort of one sentence at a time, one paragraph at a time. If you could get a paragraph done in a month, you were doing pretty good. But then saw the limitations of that the bottleneck was the supply of graduate students, which was small and finite to do all this work, to define the grammars and so on. And saw that there was so much written language that was out there, and if you could just tap into it, that would be a lot more effective than working on it sentence by sentence. And so then started to move from these grammatical techniques that go one sentence at a time to the statistical techniques that could take advantage of all this data, and kept on going from there.
And your favorite example of?
Let's see, I guess this week we had a nice launch of the music recommendation system. I think that was a fun example because it combines so many different things. That we've got the actual data from the music itself, the sounds that are there, or the bits that represent the sounds that are there, and the various Fourier transforms of it to pull out musical features. Then we have the metadata of the names of the artists and the genre and the title and so on. Then we have the metadata of everything that's been written on the web about those artists. And then finally, the social data and the recommendations of people who like this also like that. And so I think that was a great challenge to be able to put together these very diverse sets of information and come up with a recommendation system that so far people seem to like.
Yeah, so I think there are maybe two aspects of my life that really sort of got me interested in big data and sort of keep me here. One is a job I had as a sophomore and as an undergrad. This was 30 years ago in the 80s when Lotus was just coming out, and had a job to enter a bunch of data and just get it all structured. And as I started looking into it, I saw there are macros here, and Lotus has really nice visualization capabilities, and I started putting that two together. And my boss at that time was just blown away. There was sort of insights in these graphs that he had never seen before, and I quickly realized the power that there is in the numbers that are inherent. It's really hidden. You have to do stuff to bring it out. So that's a lesson that sort of sticks with me today. The other big aspect is I got really interested in how the brain works and in computational neuroscience. So that's what my PhD is on. And to me, that's kind of the ultimate learning system. And we should all build our systems, to be like that. It's, you don't have to tweak anything. It just seems to work and works on a wide variety of applications. So that's really kept me in here. I met up with Jeff Hawkins as he was embarking on Numenta, and we started this grand adventure of trying to codify how the principles behind how the brain works and create algorithms and products that kind of embody that principle. So those are kind of the two big aspects of my life, I think, that really got me interested and keep me here. In terms of kind of favorite application, we're all entrepreneurs here, so let me pick something really small but has a big vision. There's a company called Rest Devices, which is in Boston. And what they're doing is they're making clothing for babies. And what this onesie does is it's got sensors that can monitor the breathing rate of your baby, the temperature, the sound, all these kind of biometric signals. And then they send that data off to the cloud, and you have an app that allows you to monitor the baby, and it can give you alerts if there's something going wrong, and so on. And just think about the potential of that. Your baby is now a cloud-connected device with an API. How much cooler can it get?
It's the future of big data.
Yeah, so. And there's so much stuff you can do with that.
Srivas?
So I was at Google working on search. And what was very interesting in Google was the insistence on no human training when search runs. That is, it has to understand the data on its own. When somebody types in a query, go and try to understand what the person is trying to find. And I think you've seen where Google has gone with search. So that totally caught my imagination. And then this other thing called Hadoop was kind of taking shape. And so about 4 years ago, I left Google to start MapR. Very happy to say we are the best Hadoop distribution on the planet. And it's been adopted everywhere. And I think the classic example of big data making a huge difference in people's lives is actually, I'm Indian, and it's very close to my heart, is the Aadhaar UID program in India, where it's like, Indians don't have a social security number. So Nilesh Niketan from Infosys started this thing about fingerprinting and retina scanning the entire Indian population. And that's become the basis for almost all work in India for things like opening a bank account, getting your LPG gas, getting access to education, getting access to food, medicine, healthcare, small business loans, everything. And that's all running on Hadoop today. And that's very impressive because the cost at which they are doing, they've already scanned, and I don't know if you're aware of being here, they have scanned about 300 or maybe 400 million people have been fingerprinted and scanned. They'll probably be at about 600 million by the end of this year, and I think about entire 1.2 billion in another year to year and a half. And it's very impressive amount of data. And the main use of big data here is to combat the fraud that's in India. The fraud that happens in India is incredible. And what they're doing is they're tracking everything, right from who took the fingerprint on what equipment, when it happened. It's audited to the nth degree. Any use, any access of it is recorded forever. So if there's anybody who tries to game the system, will be literally tracked down and punished. So it is a very interesting use of big data, and I think MapR has donated all the software for that out there. And we are helping them to roll it out. It's very impressive to know that in India, they started this project about 4 years ago on Hadoop, well before everybody knew what is big data, what is Hadoop out here. So I think it's very close to my heart on how they're doing that. It's very impressive.
Thanks, guys. Yeah. So, when you talk about the future of big data, we all know that it starts with the data. And if you go back into the past and see where the data came from, originally it was in companies, then the web came along, and that was the big data, and Google was built on that. And then everybody's analyzing social, local, mobile data these days, and so on. So these are all the big rage today, right? But if you sort of go forward over the next 5 to 10 years, what do you see as the next big sources of data on which huge amounts of innovation are going to happen? The next set of applications are going to be built.
Yeah, I guess we're seeing a lot more of sensory data that, we used to have textual or numeric data that was in databases, and now we've got images and videos and sound recording and, the temperature of the baby and so on. And I think we'll see more of that people will be much more embedded in this network of sensors and making sense of that will be where the applications are rather than just making sense of your sales data or whatever hard numbers there were.
I actually couldn't agree more. I mean, it's probably the #1 source of new data that's going to come out over the next 5 to 10 years is all the sensory data from devices of all types and even people, such as babies. And, my doorknob is now on the internet. I installed this thing 2 weeks ago. I can now check it. It can alert me if something unusual is going on. Why isn't everything in my house connected? And that is happening. The cost of connecting sensors that connect anything to the internet is becoming so low. It's becoming extremely feasible. They're low power. They're cheap. And that source is exploding. And by some accounts, I think it's going to be like 50 billion new sources of information just coming from that phenomenon.
I mean, I totally agree. I mean, everything is a sensor from that matter, right? But I think what you're also seeing is, I think kind of I alluded to that, it's a great way of learning what's actually happening. I think that's what it ends up being, is that the data will tell you the story. That is, you don't have to sit down and hire an expert. You don't have to have somebody coming in telling you, oh, this is how this is going to work. Well, the data will tell you. We don't have to sit down and the facts, they may be inconvenient, but the factual knowledge will increase so much that anybody can go and see this now. It kind of democratizes data. It is nothing, it's not a privy to somebody, hey, I worked on this for 15 years, I have 10 degrees, I'm hiding behind. Versus, hey, I'll just go and look at the data, it'll tell me what's going on. So it's kind of democratizes the learning process. Of course, it comes through sensors, but that's what I see happening, really.
Right. So when you're dealing with these new sources of data, like sensor data and various other new data sources and new kinds of applications that we're going to deal with, if you look at the models that we're using now for modeling big data, they've all pretty much come from machine learning and statistical modeling and so on. Do you think there's fundamentally new models that, ways of looking at data that will evolve over the next few years, perhaps, based on neuroscience or deep learning or any of these technologies? And, what applications do you think that are, not being well served today by today's models could be served by such models in the future? Mm-hmm. Any of you want to take it?
Okay. Yeah, so I'm certainly very interested in the deep learning model. So this is a hierarchical model where you start at low-level features and then you have the system learn its own mid-level features and all the way up. We've been able to apply that at Google. We built a big system to do that. It starts off with images, and it notices that there's lines in the images, and that the lines come together to form corners, and then that you get like eyeballs and noses and faces and so on, sort of all the way up. So I think this is exciting to say that sort of all of big data now is focused on feature engineering, and the more the system can do it itself rather than having to have clever engineers do the feature engineering, the better. And I think this is one step in the right direction. But I think it still doesn't get us far enough because it's multi-level, but it still has this idea that what you get in the end is a bunch of attributes with weights on them for which one's more important than the other. And you don't get a more structured representation, right? So it's still sort of a vector of features. And I'd rather have like a network or graph of features, of this is related to that, in not just a hierarchical way, but in a temporal way and in a relational way. And I think we haven't quite bridged the gap there. We have great techniques for these database rows and column type approach, but we don't have very good techniques for these more graphical network type approaches. And I think that's the next horizon.
Mm-hmm. So I definitely think the analytic and algorithmic paradigm needs to change pretty dramatically in order to deal with these new streaming data sources. Many of the insights that you can get from studying the brain and studying how the neocortex works can really apply, I think, very nicely to that. So, when you have so many sources coming in, streaming dynamically, the models themselves have to be very dynamic. And the brain is fundamentally a predictive mechanism. We take data in and we're constantly making predictions. The models have to do the same thing. And as you see the data that actually comes in, if they're different from your prediction, the model should automatically adjust. So this idea of having a continuously predictive, continuously learning algorithm I think it's a paradigm that's not really very common in machine learning today that really needs to happen in order to really work well in this streaming domain. The other side of it is you need a tremendous amount more automation than we have today. Today, the process of building an algorithmic model or an analytical model is extremely cumbersome and manual. When you have so many data sources and each data source has unique properties, you need to create models that are specific to each source. That whole process has to become automated. And that's another kind of paradigm shift that I think that the analytical industry needs to go towards.
So actually, it's a very interesting question. So you can draw, big data lets you draw correlations in a large scale, and you can draw correlations between anything, and still have to be guided by common sense, in the sense that we've always heard of, hey, this vitamin, take more vitamin D, this is going to stop something else, or these medical research that's been happening in the last. We've been used to this every day. We hear something on the news that says, hey, if you take this and you do this, then your probability of your longevity increases by so much %. And those are really statistical models that somebody put together in a lab and said, okay, let me correlate these sets of things with those sets of things and say, okay, maybe if I avoid fatty food and no cholesterol for a while, then maybe I'll live longer. And that's just correlations being done. They actually didn't go and really, it's somebody else's study they brought together and put it together. Of course, the very famous example that I think was that physicist from Chicago. He showed that the number of pianos being bought and the number of deaths increased simultaneously. So you correlated those two. So you say pianos are the cause of death, right? So you can correlate any nonsense, right? I mean, so what you have to really look at is draw the correlations correctly based on what the data is. So that, I think, big data hasn't gotten there yet. And I think once it starts getting there, then you'll say learning is happening at this point. So I think it still needs to get there, and I'll be interesting to see how it gets there. Yeah, I think it was Fermi who said that. Now I remember, it was Fermi who said that. Right? Yeah.
As you look at these kind of new models, that need to be developed, and also some of the problems that you mentioned, if you keep those in mind and look at the current state of the big data infrastructure, both hardware and software, right? What do you see as kind of the biggest gaps in the infrastructure that you think will be addressed over the next few years that will enable applications, of the sort that you just mentioned?
Want to take that?
Okay. Yeah, go ahead.
So I think we saw that in one of the biggest challenges that's always been there for data is the silos of data. That is, the video stuff is in its own silo, the SQL stuff is in its own silo, the streaming data is in its own, everything is a silo of data. And the biggest problem has been trying to make sure you're seeing all the data, that you're not looking at only a portion of it and drawing conclusions. And I think the biggest challenge is to try to make I think this is like a nirvana for almost everybody. I think Google has gotten there as close as possible so far. But I think trying to have one common platform on where you can keep all kinds of data and yet access it with very different and heterogeneous means based on what kind of application you have in mind, but yet make sure that you're looking at all the data without ignoring something. I think that's kind of the, like I say, it's a utopia for most companies and most organizations. I know Stonebraker will completely disagree with me when I say that, because he builds one for each.
He's not here now.
He's not here, so I can say that.
So let me respond to that. So I think you're right that Google has done a good job of being able to share at the data level and at the program and interface level. But at the application level, I think we're still not there yet.
Yeah.
So we've got 4 different systems to find synonyms for words, because the synonyms you want to find when you're doing ads is different than the synonyms you want to find when you're doing search. And we haven't found a way to say, can you build one system that does it all and then specializations?
That I disagree. So I think you want a common data platform, but yet a complete heterogeneous stuff on top. Because each person is going to find that exact set of things that they need for their application. So the synonyms for ads has certain requirements in terms of speed and in terms of how many queries per second and so on that you don't really necessarily have in, let's say, autocomplete or something in something else.
Yeah.
So I think the requirements are different. So you do want to support heterogeneous applications, right? Something that's streaming data in, for example, stock quotes, where you have a whole bunch of synonyms there as well. That's like in the millisecond. I mean, they're counting it in under milliseconds, right? So the requirements are different. So you do want to support a whole variety of applications. But I think you want to be able to get to all the data. Like, for example, if it's coming in through one system, every other system should be able to find it if necessary, right? And that's where I think you need a common data platform. I think would be the grand vision out there. I think it's not there yet. But go ahead. I mean, you might have other opinions.
I guess my point is as we add new features, right? So we're doing a lot now with what we call the knowledge graph, which is pulling out this kind of semi-structured data and adding that as a source on top of these kind of word association type data. You hate to have to duplicate effort to say, do I want to have to do this 4 different times for my 4 different systems? You'd like to just do it once and then have each system be able to tap into it.
Yeah, except you get it wrong, I'm going to not use your system.
That's right.
So then I'll build my own. So that's the main challenge. And plus, you won't get it right. You cannot anticipate what I want.
Yeah.
Right?
Yeah, I guess everyone's trying to build a standard platform, and then they build just, now there's X+1 standards at the end of it.
Yeah.
Standards always follow the leaders.
Yeah.
I mean, I've never seen a standard that said, okay, I'm going to standardize, and then applications are built. It's always the applications are built, and then the layers are understood, and then the standard guys come and say, okay, now let's make a standard.
Yeah.
Right? It's always been backwards.
So you guys mentioned some very complex models of modeling the human brain and deep learning and all that, right? And if for everything that we've heard today, the model has been Hadoop, right? Is Hadoop the right model when you're modeling the human brain and doing deep learning and stuff like that, or do we need to think very differently in terms of the software infrastructure that we need going forward?
Hadoop is extremely batch-oriented today, so that is completely at odds with how the brain works. And again, when you look at all of the streaming sensory data, I think the systems and the infrastructure need to become much more streaming-oriented and fluid. And I think Hadoop is great at what it does, and we've looked at it quite a bit at Grok as well. But it's just not the right set of technologies for this world of Internet of Things that's coming up.
So totally. So Hadoop is an application on top of this data platform, is how I look at it. Is MapReduce is a way to, so if you want to do not much interactive response, but enormous throughput, you cannot beat MapReduce. You cannot beat Hadoop. But the data it produces should be, that's what is powering search, that, as you type, Google is producing results. So it is the same system, but it is a different application on top of the data platform, is how I look at it.
Yeah.
Right? So you need Hadoop. That's the cheapest and the easiest way to get to it. Once you put data there, that's the only way, Hadoop is the only way you can find it without moving the data. Right? I mean, I'll give you an example of where this is. There was one big bank that was, when AIG went under last year, they were asked to show all their interactions with AIG for the last 10 years. And of course, it's not online, so they had put, it was on tapes in Switzerland or somewhere and so on. And they couldn't find one of the tapes. Right? And searched, they had 3 weeks, they couldn't find it. And the judge didn't believe that they couldn't find it. So they got fined like upwards of $1 billion. $1 billion fine for not finding a tape. Well, if you were a bank, what would you want to do? You would want to find that information like in 1 day and then spend the next 3 weeks not searching for it, but trying to understand where's my exposure, right? Before I go, and I have to eventually turn it over to the government. But I have to, as a bank, I would like to understand what's my exposure, right? How would I do that in any other system unless there was a Hadoop out there, where I need to be able to find 10 years worth of information without moving it out of my archival systems. Because as soon as I try moving it, I'm dead. So cost of storage is very important. How deep and cheap and deep you can get is very important. And being able to analyze it without moving it is very important. But I think you're right. I think you still need a heterogeneous set of applications to be able to do the instantaneous work you need.
So,
Yeah, I
so let me
think
tell you about a experiment we did. In our deep learning work, we had 2 teams trying to implement the algorithms that we got from Jeff Hinton, and one using the stock Google Data Center and MapReduce, and then the other team using GPUs and sort of specialized CUDA programming. And you'd think that that would be a better infrastructure for it, but it turns out the MapReduce team won.
Of course.
And that they came out ahead. Now, I think maybe they cheated because they had Jeff Dean on their team, and the other guys didn't. But you know, it takes
GPUs in a data center, are you kidding? I mean, you really want to put GPUs everywhere? Look at the heat they generate.
That's right. So it just was easier to use what we have than try to build something custom.
So I don't disagree with anything either of you said. So Hadoop definitely has its applications, but all of that, those are batch applications that we ran. You know, some of the stuff we're doing with customers, you know, we're working with you know, Enernoc, which is a smart meter company, and we need to build a custom model for every single smart meter for every single facility that they manage. And the models are fairly small, and this problem is embarrassingly parallel. There's absolutely no need for MapReduce. MapReduce doesn't help you. Instead, you need processes that are constantly running, getting data at a fairly high rate and making predictions. So again, I think you have to use the right tool for the job. And Hadoop and MapReduce definitely has a lot of use cases, but they're also in the streaming, high velocity, high prediction world. It's not clear exactly where that fits in.
So you need a micro batch framework in some sense. That is, as soon as data arrives, well, in the next, I gather the data for the next second or so, and then make a decision based on that data gathered in that second.
Yes.
I mean, for example, the automatic driving that Google has come up with, when they drive a car automatically, right? That's doing micro batches. It's trying to analyze the video feeds and all the sensory information, but it's not doing it, one data point at a time. It's still doing MapReduce, but it's doing in micro batches. So you cannot do analysis with one data point, firstly, right? You need many data points.
Yeah, but that doesn't necessarily mean you need MapReduce.
But
that's just one computational paradigm.
But it is a great, what's micro batching, right?
So that's a great discussion that you guys should continue to have outside.
You said you wanted some context.
Yeah, I do, and I think we got some. But I wanted to throw in, move on to the next topic before we run out of time. And this is, on a completely different note, if you look at the impact on society of all this big data work that's going on, I wanted to ask about, as people get more and more used to using big data to make decisions, and that becomes the norm, what happens to the role of human beings in decision making, right? Is there room for human intuition in decision making anymore after we start using big data? I recently saw this thing where Hollywood movies are now made using big data to figure out what scenes to put in and so on. Is there a chance that we are going to get mediocrity as a result of people using data to analyze everything to death? Is that going to cause a backlash against big data at any point?
Well, I think a lot of the big data is made from people. It's like Soylent Green, right? So it's things that people say or do or write or have pictures taken of or decide to point their camera at. And so it's their choices that are going into it. So I think it's a summary of all these personal decisions rather than an elimination of them.
I think people always need to be involved in the decision making, and my hope is that with big data and with these technologies, we can make those decisions a lot more informed than they are now. Much of the decisions that people make today are based on intuition or hunches or looking up something or looking at past behavior. But my hope is with these tools, we can give a lot more of the insight into what's there in the numbers and maybe give possible predictions, and we can really assist the human in making much better decisions than what they're doing today.
I think the first social impact of big data is what we're seeing happening in India right now. There are 1 million, the Aadhaar program, which I talked about in the beginning, already has, they have installed 1 million ATM machines that can read your fingerprint and put money in, touch it, and you get a prepaid credit card that you can use anywhere. So it's a pretty incredible thing they have done with big data. That is, it's used to combat fraud. People are scared of that. A person's, all 10 fingerprints and 2 retina scans is about 10 to 15 megabytes per person of data, multiplied by 1.2 billion, right? to look that up quickly on every authorization for food or for education services or for medicine or for, you go to a dispensary and they give you medicine or give you access to a doctor. And then they know it is you. They can follow your history of what happened to you, in terms of your medical history. That's an amazing use of big data. It's also getting there with micropayments, paying through your cell phone, because many people don't have bank accounts. All they have is a SIM card. All over the world, they're watching what India is doing with this. I think all over Africa, all over South Asia and Southeast Asia. So I think that's a pretty powerful way to use big data, is to make sure that nobody can cheat and make it enable it to maybe give access to everybody. I think it's a pretty amazing use.
And we've run out of time. I'd like to thank the panelists, and we'll come back in 5 years and check their predictions to make sure whether they got it right. Yeah. Thanks, everyone.
Thank you.